Okay, let's dive right in. Look at this terminal boot up sequence. It's time to initiate our journey into mastering dynamic memory allocation in C. If you've been writing C code, you probably already know the basics. But today we're unlocking the true, completely unrestricted power of the language. Welcome to this explainer. We're going to demystify the stack, conquer the heap, and really get into the true power and, honestly, the serious consequences of manual memory control. By the end of this, you won't just be writing code. You're going to be commanding the very hardware your code runs on.
We really need to understand where your code actually lives when it executes.
So notice the clear physical distinction going on here. Over on the left, you've got the slow, permanent vault of the hard disk. That's where your source files and photos live. But when you execute a program, it gets copied over to the right side, right onto the incredibly fast temporary workbench of your RAM. Now, RAM is super fast, but it is finite. And as you probably know, it's completely wiped the second the power goes out. Now, if you look closely at how that RAM workbench is specifically sliced up for a running C program, you'll notice a distinct vertical layout. At the top, growing downwards, we have the rigid automatic stack. And then right there in the middle, growing upwards, is the expansive manual heap. This physical separation, it's absolutely crucial. It's the key to understanding exactly why dynamic memory is so incredibly powerful. To really cement this difference, think of the automatic stack like a small disposable post-it note. You know, it's fast, it cleans up after itself, but its size is totally fixed at compile time. It's kind of like reserving a fixed dining table before your guests even arrive. The heap, on the other hand, is completely manual and determined at runtime. Think of it like renting a storage locker. You hold the key, and it stays yours for as long as you pay for it, or in our case, until you explicitly free it. Basically, it's like dynamically renting extra chairs as more people actually show up to your party. Why would a programmer ever want to leave the cozy safety of the stack? Well, the crucial point here is that you are practically forced to use the heap under 3 specific conditions. First, when you're dealing with unknown data sizes. Second, when you've got mutable structures, like arrays that actually need to grow or shrink during execution. And third, for function survival. That's when data absolutely must persist beyond the life of the specific function that originally created it. To put that into perspective, if you have absolutely no idea whether a user will ask for 5 or 500 records until the program is actively running, well, the fixed size of the stack simply fails you. Similarly, if you're building flexible data structures like linked lists or binary trees, that data has to survive after the local function returns. So the heap is literally your only option. To solve this, we fire up the engine of allocation, malloc. Check out the golden formula highlighted here. You request memory by multiplying the number of elements you need by the size of your specific data type. And this is vital. Look closely at lines 3 through 6. You absolutely must always check if the pointer returned is null. If the system is out of memory, malloc is going to fail. If you don't catch that null pointer, your program is going to crash. No way around it. Notice how this abstract syntax literally maps right onto the physical memory grid. When you call malloc for 3 integers, the system goes in, carves out a contiguous block of space big enough for them, and it hands you back a single pointer to the very first byte of that block. Also, just a quick note on the detail at the bottom about typecasting. Modern C allows implicit casting of the void pointer, whereas traditional C requires explicit casting. Just a neat little detail to keep in your back pocket. Now, as you level up, your toolkit is going to expand well beyond raw malloc. See, malloc gives you raw blocks, but they might contain leftover garbage values from whatever was there before. If you need a completely clean slate, you use calloc. That strictly initializes all memory bytes to 0. Just pay close attention to that comma syntax instead of the multiplication star. And what if your needs change? Well, realloc lets you expand or shrink a previously allocated block on the fly, all while retaining your original data. It's a real game changer. Renting this massive power comes with the uncompromising burden of cleanup. And this brings us to the price of power, the free function. Using malloc is exactly like borrowing a limited library book. Think about it. If you take out books and never explicitly return them using free, eventually there are just no books left for anyone else. So best practice here is absolutely paramount. You must always release the memory and immediately set your pointer to null to strip it of its access rights. To wield this power safely, you have to strictly follow these 4 non-negotiable steps for every single allocation you make. 1. Request the space. 2. Verify the success of that request. 3. Actually do your work. And 4.
always end by returning the memory and resetting your pointer. If you skip a step, you are literally inviting disaster.
Take a look at this continuous loop. The absolute golden rule of C is right there in the center. Every single malloc must have exactly one matching free. Whatever you pull out of the system, you must actively return when you are done. No exceptions. But what happens if you get careless? Code failures on the heap manifest as these three terrifying villains. First up, memory leaks, which are caused by simply forgetting to free memory. Second, dangling pointers. That's where you try to use a pointer after it's already been freed, causing undefined behavior and silent data corruption. And third, the double free, calling free twice on the exact same pointer. This immediately triggers a fatal error and completely aborts your program. Let's precisely define the most insidious villain of them all, the memory leak. A memory leak is like a silent sickness. It happens when you forget to call free, causing your program to perpetually consume more and more RAM over time. It just keeps eating it up until the entire operating system begins to slow down, stagger, and eventually crash. Watch the diagram here to see the anatomy of that leak in action. So we allocate block A, but then we reuse the exact same pointer variable to allocate block B without freeing block A first. By casually overriding that pointer's address, block A is lost in the void forever. The system still thinks it's being used, but you don't have an address to access it or free it anymore. It's just dead weight. Fortunately, you don't have to fight these villains blindly. We can hunt them down using a super powerful terminal detective called Valgrind. You just wrap your program execution in Valgrind, and it acts as an active memory error detector. Look closely at that highlighted output at the bottom. The phrase "definitely lost" is the absolute smoking gun. If you see those words, it means you successfully allocated memory, but you completely missed a matching free. To keep you sharp, safe, and efficient, here is your master's reference card. This perfectly summarizes everything we've covered today, from the proper multiplication syntax of raw allocation to the comma delimiter of calloc, all the way to safely nullifying your pointers right after freeing them. Keep this matrix in mind whenever you leave the stack. All right, now it's time to actually solidify your mastery. Here is your final blueprint practice program. I highly encourage you to pull up your editor and actually build this. It requires you to ask a user for a number, dynamically allocate that exact amount of memory, do some work by reversing the numbers, and then successfully clean it all up. It serves as a stark, practical reminder that every single block you rent, you absolutely must actively return. The dynamic power of the heap is now entirely in your hands. You've got the tools, you have the syntax, and you understand the physical mechanisms at play here. But the ultimate question remains. As your programs grow and scale, will you remember to free it? Thank you so much for joining me in this explainer, and happy coding.